Okay, thank you. And this topic is about creep rupture models for austenitic stainless steels. And I'm Junjing He. This work is together with my supervisor, Professor Rolf Sandström, and we are from KTX. This report contains the introduction creep rupture models and the results and the summary. For the current ultra-supercritical fossil fuel-fired power plants, the aim is to increase the temperature to 700 to 750 degrees in order to improve the operating efficiency as well as reduce the carbon dioxide emission and all the environmental pollution. However, the life of the components in these conditions is limited by the properties of the materials, especially the creep strength and oxidation resistance. What happened?
You press the black.
Oh, sorry. Austenitic stainless steels with high creep strength are widely used in the power plants. Therefore, it's important to understand the life-controlling rupture mechanisms in these steels. In general, for creep failure, it can proceed in two modes. It can be brittle rupture and ductile rupture. And for ductile rupture, the main mechanism is dislocation recovery. And for brittle rupture, which is due to the creep cavitation, it can be resulted from the formation, growth, and coalescence of creep cavities at grain boundaries. So in order to model the creep rupture at high temperatures, the main aim of this work is to propose models that can reproduce the creep rupture of austenitic stainless steels without any fitting parameters. The grain boundary sliding is considered as the basis for creep cavitation models. So two grain boundary sliding models have been presented for austenitic stainless steels, and where it's related to the creep rate by parameter Cs. And this is the equation. The parameter Cs is grain size dependent in the shear sliding model. Here is the results of the grain boundary sliding models, and this figure shows the comparison of the shear sliding model and the experimental grain boundary sliding displacement as a function of creep strain for different types of austenitic stainless steels. The lines here are the average value of the modeling and the experimental results. So the modeling results, it can show good agreement with the experimental data. And with the grain boundary sliding models, it's possible to propose the cavity nucleation models. A double-light model has been proposed for cavity nucleation, and where cavities are generated at intersections of subboundaries with subboundary corners or particles due to grain boundary sliding. And the mechanism is like this: when the here it's when the subboundary corners or particles on one side of the sliding grain boundary meet the subboundaries on the other side of the sliding grain boundary, the cavities will be generated. So based on this mechanism, we have proposed the cavity nucleation rate, and they can be related with here CS is the grain boundary sliding parameter, and also this up here is the subgrain size, and along here is the interparticle spacing. The final form can be written as parameter B times the creep rate. And here it's the results for the cavity nucleation models. This figure shows the cavity number per unit grain boundary area as a function of a creep strain. So as you can see here, it's for different types of austenitic stainless steels. And the lines here, this is the modeling results, and this is the experimental average values. And it's very evident that there is a considerable scatter in the experimental data, but the model still gives a reasonable representation of the experimental behavior. And the modeling average value, it also agrees well with the experimental average value. Now we can go on with the cavity growth model. For growth of creep cavities, modified constraint cavity growth model has been proposed, where the constraints from the deformation rate of the surroundings have been taken into account. So for the final equation of the cavity growth model, so it's related to grain boundary diffusion parameter, and Kf here is a factor which is a function of the cavitated area fraction. And sigma 0 here is the sintering stress. Sigma red here is the reduced stress. And mainly in the modified constraint cavity growth model, we have calculated the reduced stress with the help of FEM. And the affected rho of the reduced stress is approximately equal to the cavity diameter. And finally, the reduced stress could be derived from this equation. And here, the L is the cavity spacing, and this is the creep rate at a reduced stress. Here we shows the results for the modified constraint cavity growth models. So this is the results of the new models. And here is the cavity growth rate as a function of creep time. And both the modeling and the experimental results demonstrated the same trend with increasing creep time. And also the modeling cavity growth rate, the lines, it lies in the same range of the experimental data. And also here it's the cavity radius as a function of creep time. It's for 18 chromium 10 nickel austenitic stainless steels. So it's very clearly that the modeling cavity radius lies fairly well in the center of the experimental ones. And also identical results have been obtained for other types of austenitic stainless steels like 321 and 347. Now with the nucleation and growth of creep cavity models, it's possible to predict the brittle creep rupture. It's assumed that creep failure takes place when the fraction of the cavitated area reaches a critical value, and the area fraction of cavities on the grain boundaries can be expressed as an integration of the cavity nucleation and the cavity growth. It's the cavity radius. So with the combinations of creep cavity nucleation and the new cavity growth models, the brittle creep rupture can be obtained. Here we shows the results for the brittle rupture models. And this is the creep rupture strength as a function of creep time. It's for 321 austenitic stainless steels. The experimental data here is in a range of 600 to 750 with 50-degree interval. And the experimental data is from NIMS, it's from Japan. The modeling results here is based on the creep cavitation models. So the results at a longer creep exposure time, it can reach a good agreement. But on the other hand, there is also the ductile rupture behavior, and where the fundamental models have been used. And here is the fundamental model that has been well developed for dislocation creep of austenitic stainless steels. It's related to the glide and climbability of dislocations and precipitation hardening and the stocking for the energy. I will skip the details here because it's a well-established model and also available in many of our published papers. Here is the results for the ductile rupture models, and the experimental data is still the same data, but the model is based on the fundamental models that's based on the dislocation creep. So here the ductile rupture models can predict the overall behavior of the creep rupture curves, and also it shows better agreement at higher stresses. Then to predict the creep rupture, it's to combine the brittle rupture and the ductile rupture models. So when taking both models into account, the simple principle is that the type of failure that is predicted to take place first is assumed to be controlled.
2 minutes.
And here is the final results for the creep rupture. This is the rupture prediction based on the combination of the two models. So by taking the brittle rupture into account, the prediction of creep rupture for long time is improved. So one can see there is two reasons in the figures. And also similar results have been obtained for other types of austenitic stainless steels like type 304, 347, and 360. Summary. For creep cavitation, a green boundary sliding model, cavity nucleation model, and a modified constraint cavity growth model have been proposed. And the model results show good agreement with the experiments. And based on the creep cavitation models and the dislocation creep models, the creep rupture strengths of austenitic stainless steels were predicted quantitatively. Yeah, thank you for your attention.
Thank you very much.